This lecture video kicks off Chapter 11 with the goodness of fit test. The goodness of fit test is used to test the hypothesis that an observed frequency distribution fits or conforms to some claimed distribution. One of the examples that we'll do involves Benford's law. Benford's law gives the expected occurrence of leading digits for a genuine set of numbers. It states that the numeral 1 will be the leading digit 30.1% of the time. The numeral 2 will be the leading digit 17.6% of the time, and so on. You can see in this table the percentages or proportions of the time that each digit will be the leading digit. The example that we will look at will involve checks being written by companies that seem slightly suspicious. The idea is that if the observed frequencies that we have line up with Benford's law, then things seem to be okay. But if they do not line up with this law, then we have reason to be suspicious, or then we have reason to suspect fraud. That's the idea of comparing an observed frequency distribution to a claimed distribution. The goodness of fit test will tell us how close is close enough and how different we would need to be in order to say that there's a significant difference. Let's talk about notation and requirements for this type of test. Capital O represents an observed frequency, while capital E represents an expected frequency. K is the number of categories or outcomes that the frequency distribution is broken into, while N is the number of trials, the sum total of all the frequencies. Lowercase p is the probability that an individual sample value falls within a particular category. And the degrees of freedom in this case will be calculated as k minus 1, the number of categories minus 1. Notice that this is not n minus 1. We do have 3 requirements. The data must be randomly selected, and the sample data must consist of frequency counts for each of the different categories. We don't want averages or anything else, just counts. The expected frequency should be at least 5 for each category. In other words, each value for E, the expected value, must be greater than or equal to 5. With a goodness of fit test, the null hypothesis is that the frequency counts agree with the claimed distribution. The alternative hypothesis is that the frequency counts do not agree with the claimed distribution. The test statistic is a chi-square statistic, and it's calculated like this. We take each observed frequency and find the difference between that value and the expected frequency for that category. We square this difference and then divide by the expected frequency. Once we've done that for each category, we add them all up, and that's our test statistic. If you have a TI-84 calculator, you can use the chi-squared goodness of fit test, but I will show you how to do this without the TI-84 calculator. Critical values and p-values can be found using the chi-squared table, as well as other functions in our calculator. It's also important to note that a goodness of fit test is always a right-tailed test, and if for some reason a significance level is not given, we will default to a significance level of alpha equal to 0.05. Let's take a look at our first example. In this first example, we're going to use a 0.05 significance level to test the claim that occupational injuries and illnesses occur with equal frequency on different days of the week. Whenever you see the phrase equal frequency, that's your clue that what we're really talking about here is a uniform distribution. They expect the frequency to be the same across all categories. In this example, the categories are the work days, Monday through Friday, and we are given observed frequencies in terms of number of injuries for each of those 5 days. Let's think about what is being claimed. The claim is that the frequency is the same for each day. In other words, this claim is that we have a uniform distribution. If we add up all of the frequencies for all of the categories, we have a total number of injuries, n, equal to 107. If we had equal frequency across all 5 days, we would expect 107 divided by 5, or 21.4 injuries per day. That's the expected value for each day. Let's add the expected values as another row in the table. We expect there to be 21.4 injuries on each day if this does conform to the claimed distribution. Just taking a look at the observed values and the expected values, they aren't that far apart. The goodness of fit test will tell us if they are different enough to say that this is not a uniform distribution. So let's get started with the null and alternative hypotheses. The null hypothesis is that the observed frequencies do conform to this claimed uniform distribution. That is, the probability of having an injury on each of the 5 days is equal. The alternative hypothesis is that it does not conform to the claimed distribution. In other words, at least one of these is different from the others. The second step is to calculate the test statistic. The test statistic, chi-squared, is equal to the sum of the differences between each observed value and the corresponding expected value squared divided by the expected value. Let's start by putting our observed values into list 1 and expected values into list 2 in our calculators. Whether you are working with a TI-83 or 84 calculator, this part of the process is the same. We'll go to Stat, Edit, and enter the observed values into list 1. Then we'll enter the expected values into list 2. If you're working with a TI-83 calculator or any calculator that does not have the goodness of fit test, your next step is to build list 3 representing the expression inside of the sum that's needed for the test statistic. We need O minus E squared. So while list 3 is highlighted, I'm going to use parentheses, list 1 minus list 2 squared. Our values for O are found in list 1 and our values for E are found in list 2. So now we have the numerator of the expression. The denominator is E and those values are found in list 2. Pressing enter will build list 3 and give us all of the values that we need to add up to have our test statistic. Let's have our calculator do that part for us too. We'll go to Stat, Calculate, and option 1, one variable statistics. We want to add up list 3. So for my list, I want to enter second 3 for list 3 and press enter when calculate is highlighted. The second value listed is the sum of all of the values in list 3, 0.5234. Let's take this back to the example. With our values for O in list 1 and our values for E in list 2, we built list 3 equal to list 1 minus list 2 squared divided by list 2. So our chi-squared test statistic is equal to the sum of all of the values in list 3, which was 0.5234. If you happen to have a TI-84 calculator that has the goodness of fit test, you can use that instead. It's called the chi-squared GOF test. We will need to input the list where the observed values are found and where the expected values are found, as well as the degrees of freedom. Our observed values are found in list 1, our expected values are found in list 2, and our degrees of freedom is equal to k minus 1. That's the number of categories minus 1. In this case, k is 5, so our degrees of freedom is 4. Let's locate this function on our calculator. We'll go to Stat, Tests, and towards the very bottom, we have chi-squared GOF test. We have list 1 for the observed values, list 2 for the expected values, and 4 for the degrees of freedom. Once calculate is highlighted, we'll press enter. Notice that this first gives us our chi-squared test statistic of 0.5234. It also gives us a p-value of 0.9712. The chi-squared test statistic that we obtained using both methods is identical. In each case, we found the test statistic to be equal to 0.5234. The next step of our hypothesis test is to calculate the p-value. Using the calculator goodness of fit test, we were given a p-value of 0.9712. However, if you do not have that calculator function, like on a TI-83 calculator, to find the p-value, we can use the chi-squared CDF function. Here's the idea. With our chi-square curve, which of course is right-tailed, We have a test statistic of 0.5234. The p-value is the area under the curve to the right of the test statistic. The chi-squared CDF function will ask for a lower limit and upper limit and degrees of freedom. The area that we want has a lower limit of our test statistic, 0.5234, and since infinity is not an option for the upper limit, we'll just put a really large number. We'll also enter our degrees of freedom of 4. Let's head back to our calculator. We can find the chi-squared CDF function by going to second vars to get into the distribution menu. Scrolling down a ways, you'll find chi-squared CDF and press enter. We'll put in our lower limit of 0.5234 and our upper limit. We'll also put in our degrees of freedom of 4. When paste is highlighted, we'll press enter. Depending on your type of calculator, chi-squared CDF may not have opened up a menu. It may have instead entered chi-squared CDF and parentheses onto the screen of your calculator. If that's the case, simply type the lower limit, upper limit, and degrees of freedom separated by commas. Pressing enter gives us our p-value of 0.9712, the same p-value that you would have gotten if you had the goodness of fit test on your calculator. With this large p-value equal to 0.9712, we are clearly larger than alpha, 0.05. Our observed frequency distribution is not significantly different from the expected frequency distribution. In fact, the critical value in this case is 9.488. That's the chi-square value that corresponds to a right area of alpha equal to 0.05. So our test statistic would need to be larger than 9.488 in order for us to reject the null. So what is our conclusion? We have a large p-value, much greater than alpha. So we fail to reject the null. While we cannot conclude that it's the exact same for each day, this test has given us no reason to believe that it's significantly different. So informally, we might support the idea that occupational injuries and illnesses occur with equal frequency on different days of the week. Now let's take a look at our example dealing with Benford's law. This example gives us the backstory that when working for the Brooklyn District Attorney, investigator Robert Burton analyzed the leading digits of the amounts from 784 checks issued by 7 suspect companies. The frequencies were found to be 0, 15, 0, 76, 479, 183, 8, 23, and 0, corresponding to the digits 1 through 9, respectively. Here's the big idea. If the observed frequencies are substantially different from the frequencies expected with Benford's law, the check amounts appear to be the result of fraud. We're going to use a 0.01 significance level to test for goodness of fit with Benford's law to see if these checks might be the result of fraud. Let's organize the given data in a table. We are given the observed frequencies for the digits 1 through 9 as 0, 15, 0, 76, 479, 183, 8, 23, and 0. And what we expect is that these frequencies would follow Benford's law. So let's think about what the claim is. The claim is that the proportions are the same as Benford's law. We have a total N of 784 checks. And we have a total number of categories, K, equal to 9, 1 for each of the digits 1 through 9. That means our degrees of freedom will be K minus 1, or 8. If we conform to Benford's law, we expect 30.1% of the checks to have a leading digit of 1. So our expected value for the first digit is 0.301 times 784. This gives us our first expected value of 235.98. Since we would expect 17.6% of the checks to start with a 2, we can find the expected frequency for these 784 checks by calculating 0.176 times 784. This gives us our second expected value of 137.98. We expect 12.5% of the checks to have a leading digit of 3. And with 784 checks, that means we expect 0.125 times 784 to start with a 3, or 98. And continuing in this way, we can find all of the expected values. I took each proportion given by Benford's law and multiplied it by 784 to get all of our expected values. Look at how different the observed values are from the expected values. This should already give you a clue as to how this hypothesis test is going to go. The first step in our hypothesis test is to figure out the null and alternative hypotheses. With a goodness of fit test, the null hypothesis is always the idea that the observed frequencies conform to the expected frequencies, that they are equivalent. So in this case, we'll need to say that the probability of a check beginning with 1 is 0.301, and the probability of a check beginning with a 2 is 0.176, and the probability of a check beginning with 3 is 0.125, and so on. The alternative hypothesis, on the other hand, is the idea that at least one of these is different. Step 2 is to calculate our test statistic. We'll start by putting our observed values into list 1 and our expected values into list 2. With our chi-squared test statistic equal to the sum of the difference of each O and E squared divided by E, we can build this sum using the list in our calculator or use the goodness of fit test. Regardless of whether you have the goodness of fit test or not, the first step is the same. We go to Stat, Edit, and enter our values into list 1 for the observed values and expected values, being sure to first clear out any old data. I'll start by going through this process, assuming that we do not have the goodness of fit test function in our calculator. We will build list 3 to be the difference of each O value and E value, list 1 minus list 2, squared, divided by the expected value, the values for E found in list 2. Now our test statistic is the sum of the values in list 3, which we can find by going to Stat, Calculate, one variable statistics, and list 3 as our list. Pressing enter when calculate is highlighted, we find our sum of 3,650.243. We created list 3 as list 1 minus list 2 squared divided by list 2. That meant that our test statistic was equal to the sum of the values found in list 3, or 3650.243. If you have a calculator that can run the chi-squared goodness of fit test, the process is a little different. We'll go to Stat, Tests, and scroll down to the chi-squared goodness of fit test. We have our observed values in list 1 and our expected values in list 2, but this time our degrees of freedom is 8. Once Calculate is highlighted, we'll press Enter. This gives us our chi-squared test statistic of 3,650.243, the exact same test statistic we just found using the other method. Notice that this also gives us a p-value equal to 0. Let's take this back to our example. The chi-squared goodness of fit test required that we inputted our observed values, which we have in list 1, and our expected values, which we placed in list 2. We also needed to enter our degrees of freedom equal to 8. This gave us our chi-squared test statistic of 3,650.243. It also gave us our p-value, which we'll use in the next step. Step 3 of our hypothesis test is to find the p-value. This time our test statistic is a very large number, 3,650.243. According to the goodness of fit test, this gave us a p-value of 0. That means that rounding to 4 decimal places, the area to the right is 0. Working without the goodness of fit test, we could find this right area by using the chi-squared CDF function. We would enter our lower limit of 3,650.243 and our upper limit as a really large number. We will also need our degrees of freedom equal to 8. We find this function in the distribution menu by clicking second vars and scrolling down to chi-squared CDF. We have our lower limit of 3650.243, our upper limit of a large number, and our degrees of freedom of 8. Pressing enter when paste is highlighted gives us the view of how you would input this if chi-squared CDF did not bring up that menu. The lower limit, upper limit, and degrees of freedom all separated by a comma. Pressing enter, we have our right area of 5.1 times 10 to the negative 74th, which rounding to 4 decimal places is clearly 0. We have a p-value that we can express as 0 plus. It's not exactly 0, but it is so small that when rounding to 4 decimal places, it is 0. In this situation, the critical value is only 20.090. That's the chi-squared value that corresponds to a right area of alpha equal to 0.01. So clearly our test statistic is much farther to the right than the critical value, and our p-value is significantly less than alpha. So we're ready to write our conclusion as step 4. Since we have a p-value that is significantly smaller than alpha, we reject the null hypothesis. In other words, our conclusion reads like this. There is sufficient evidence to support that the leading digits of the checks do not follow Benford's law. In other words, we have evidence to suspect fraud. That concludes this lecture video on how to conduct a goodness of fit hypothesis test.